The biggest thing today, like I said, is I want to walk through and talk through some of the practice problems and make sure that you're in a good spot for that, that you understand what you're doing, and that, again, you can wrap it up. Wrong thing. In what we have done, we have each problem you're looking at the energy transfer. So you're figuring out what type of energy you have at the top or in one form, and then how that translates into another form to be able to solve for the missing variable. And so numbers 1 through 5, we're just going to set up and get you going on and make sure that you kind of understand the situation and make sure you have the right energy. And there's some details we might get into in that. And then 6 and 7, we'll do the whole problems together. Those are kind of goofy ones that have different layers on it that are a little bit different. So the question that we have on number 1 is, you've got a diver on a platform and they are 5 meters above the water, and is being asked how fast, when they go into the water, how fast are they going? So the types of energy we have up here, we have potential energy here, and we have kinetic energy at the bottom. Potential energy because it is the person is moving, and then kinetic energy because, or sorry, potential energy because it's above the ground, and then kinetic energy because it's moving. And so those are the 2 forms that will set equal to each other. The potential energy at the top will be equal to the kinetic energy at the bottom. And so remember your 3 types: potential if it's above a lower point, kinetic if it's moving, and then elastic if something is stretched or compressed. And so there's nothing stretched or compressed here. We just have potential up here and kinetic down there. So we can say mass times gravity times height equals 1/2 mv squared. And the thing to keep in mind is that the mass doesn't matter because it ends up canceling out. When we divide both sides by mass to solve for the velocity, it cancels out on that side, but it also cancels out on that side. And that combination then allows us just to remove it all together. So we can say gravity times height equals 1/2 times velocity squared. And anytime you're only dealing with potential and kinetic energy, your masses should cancel out. Anytime you have a spring energy, elastic energy in there, you'll need to keep the mass in your potential or kinetic as well, because it won't cancel out of the spring, the elastic stuff. So if we're solving for V, we can multiply both sides by 2 and get rid of the half. So we have 2 times gravity times height equals V squared. And then we can take the square root of both, giving us that square root of 2 times gravity times height equals our V. So that's what we get down to. Gravity is 9.81, height is 5, and you can wrap that up when we're off of here. So if you want to screenshot that, you can do that. Or if you have any other questions, please go ahead and ask before I erase it. All right, that's the first one. Number 2 we'll look at. Number 2, we have a slingshot has a spring constant of 450 newtons per meter. It's pulled back a distance of 33 centimeters and holding a stone that has a mass of 0.15 kilograms. And calculate how fast the object leaves the slingshot. So we'll be looking for V. And then, assuming the slingshot is shot straight up, calculate the height of the rock. And so this is what we have. We have our slingshot here. So that's the top of the slingshot. We're going to pull it back. We have a rock in here. And when it's pulled back, we have elastic energy. That rock will be released and is going up. So now it's not stretched out. It releases that rock. It starts going up. At this point, it's all kinetic energy. And then the slingshot's still down here, but the rock is now up here at some height. And so this is now potential energy. And we have got those 3 things that are working here together. And we need to know what is the velocity at which it's going as it leaves, and we need to know what the height is. We know the K value of the slingshot, and we know the distance that it's pulled back here. The one thing about the distance is it's given in centimeters, so we need to switch that to 0.33 meters. So now we can take and set some things equal. So for part A, We are looking for the velocity. We know the information that we need on elastic energy, and we know that it will all transfer to kinetic energy, and velocity will be a part of that kinetic energy, so we can solve for that. So we have 1/2 kd squared will equal 1/2 mv squared, and you'll solve for v. The thing that you can do here is you can cancel out the halves. You have those on both sides. And then you can divide by m. And so you'll have, this will cancel out. You'll have v squared equals kd squared over m. And you can take the square root of both sides. And then for part B, we're looking for height. So again, we know all the information we want to know with elastic energy, and it will all be going into the potential energy. You could do kinetic to potential now that you have the velocity. We're going to stick with elastic because this is what's given, and this is calculated, so it'll have more error in it because you're rounding and then putting it in and then rounding again. So we'll keep with the information that we have. So we have 1/2 kd squared, and for potential energy at the top, you have mass times gravity times height. And when we're solving for the height, then we'll divide both sides by mass and gravity. So we'll be left with the height is equal to all of that. So any questions on this one? And then also take a screenshot if that is helpful for you. And hopefully you can wrap these up as when we're off of here. These, like I said, these ones, I just want to make sure that you have the right energies that you're looking at, and then kind of get them set up a little bit. Number 3 is looking at, you have a toy popper. And so this actually would show up as, if you did the popper option on the lab, the first one, this is the same sort of idea. The mass of the toy popper is 8.5 grams. And you have a spring constant, K, is 244 newtons per meter. And the popper is compressed 2.3 centimeters. And how high will it pop is what we're looking for. So we're just looking for how high it pops. We don't have to look for how fast it's going. That's not being asked. You can. We don't need to. And so there's a couple things here that we have to think about. First, we need to get our units into the ones that will be workable within what we have. So 8.5 grams, we need to get into kilograms. And so we'll divide by 1,000. That will give us 0.0085 kilograms. And that'll be the number that we use in our calculation here. 2.3 centimeters, divide by 100. So we'll be moving the decimal place 2 to the left. So 0.023 meters. We have the popper down here where it's compressed. So we got our popper, we'll draw like our little ones at school look. There's our frog. It's compressed here, and then it's going to go from where it launches. So we have our elastic energy here, and then it's going to launch up here. It'll be uncompressed. We'll smile on the frog, and it'll be up there at the height that we have, and we'll calculate that height. And so here we have elastic energy, and here we have potential energy, and we're looking for the height. So those will be the two things that we'll set equal to each other. So we have 1/2 kd squared. We know all of that. We know the K, we know the D. And we'll set that equal to mass times gravity times height. So you'll be solving for the height, so you'll divide by both mass and gravity. So you'll be left with height is equal to this, and you have all of those pieces. I'll leave that there for a screenshot. Does anyone have any questions on those? All right, number 4, trampoline. I'm gonna draw real quick, and then I'm gonna mute and draw, and then I'll come back to it. All right, so looking at this, you have your trampoline, and it's compressed and then going fastest and then at the height. And we know that the mass is 48 kilograms. We know that the distance compressed is 0.39 meters. We know that the height equals 1.35 meters. And so we're looking at, on this one, I think it's asking for both. The first thing it's asking for is calculating the spring constant, K, and then asking for how high he's launched. And so we're looking for K and then H. No, how fast he's launched, V. So these are the pieces that we're looking for based on this information. What we do know is how high up he is, and we know the mass, and so we'll be able to use our potential energy to solve for that. So here we have elastic energy where it is stretched. Here we have kinetic energy moving the fastest, and then here we have potential energy at the top. Little fun side fact, I'm absolutely terrified of trampolines. I'm completely okay if I'm at a place like Sky Zone or something where it's all on the same level. But if I'm outside on a backyard trampoline or something, I absolutely lose my mind. I cannot handle it. And I'm always like, I'll try it. And then absolutely the heart starts pounding and I start sweating and I can't handle it. So it's just a fun thing that happens. It's super cool. Anyway, so anytime I do these, I'm like, oh, not a fan. Again, Sky Zone, fine. It's all on the same level. I don't know. It's goofy. All right. So we know that these are all equal to each other. We have our elastic energy. We don't know, but we're going to find that. We're going to use that first. So the first thing for part A, we know our potential energy, and we're going to set it equal to our kinetic energy. And so potential energy is mass times gravity times height, and kinetic energy is 1/2 kd squared, and we're solving for K. So in order to do that, we'll multiply both sides by 2 and cancel that out. So we have 2 times mass times gravity times height equals kd squared. And then we'll divide both sides by d squared here. And cancel that out, and we're left with K is equal to this. In the next part, we're looking at, for part B, we're looking at for the velocity. And so we know the most about our potential energy, so we'll set that up here. And we'll set up our kinetic energy here. So we have mass times gravity times height is 1/2 mv squared. And again, because we have masses on both sides, we can cross those out. And so we've got gravity times height equals 1/2 v squared. And when we're looking for the v, we've done this rearrangement several times. We have the square root of 2gh equals our v. So that's where we're headed on those. So in both of these, you're using the potential energy, setting it equal to the, sorry, I did the wrong one here, elastic energy here to solve for K, and then setting it equal to kinetic energy here to solve for V. And so if you want to screenshot that and ask questions, this is number 4, I think. 4, yes. Yeah. So screenshot, any questions on there? All right. We'll go on to number 5. We'll get 5 set up, and then, like I said, 6 and 7 we'll do in their entirety, and it'll hopefully get you in a good spot to wrap up the whole thing and then move on to what we're doing, or to move on to quizzes and stuff. All right, number 5. A Nerf gun is cocked back a distance of 0.6 meters. And it shoots, the mass of the dart is 0.0023 kilograms. So everything is in its proper unit already. And then we're going at a speed of 8.0 meters per second, and we're going to solve for the spring constant. So we have, with a Nerf, when you're shooting a Nerf dart, you pull it back, and you compress the spring, and then when you let it go, that spring releases. The energy from that spring is transferred into the Nerf dart, and it takes off. And so this is the situation that you have here. So with that, and when it's compressed, you have elastic energy, and when it's moving, you have kinetic energy. And so elastic energy, we know, is 1/2 k d squared, and we have the d, but we don't have the k. We'll look for that. And then kinetic energy is 1/2 mv squared. And so we take the halves off. If you're multiplying on both sides by the same thing, those will cancel. So you have kd squared equals mv squared. And to get the k by itself, you'll divide by d squared. And so you'll have k is equal to mv squared over d squared. One of the things that people sometimes want to do when they see all the squares is the first thing that they do is they go, oh, we got to take the square root of that. No, we don't. In this situation, you're taking the mass times the velocity squared divided by the d squared, and that in itself gives you k. So you don't have to do any square roots in this one because you're not solving for d or v. You'll keep the squareds with what you have here. When you're doing this, the mass is not squared, but the v is and the d is. So just kind of keep that in mind as you're calculating that. I'm going to leave that there. If you have any questions on that while you're screenshotting it, go ahead. And we'll do number 6. Number 6. Number 6 is a situation similar to what we did in class the other day. In class, we used a roller coaster example. This one, we're going to use a sledding example. So you've got someone who's running and going onto the sled. So here's your sled. They're going onto the sled to go down. And at the top of the hill, they are moving at 8.5 meters per second. And the hill is 15 meters high. And so the question is, there we go. Let's see if we can make it. The question is, how fast are they going at the bottom? And so at the top, you have potential energy because you are above the ground. So mass times gravity times height. And you're also moving, so you have 1/2 mv squared. And at the bottom, I'm going to say v top squared. And at the bottom, you have 1/2 mv squared v at the bottom. This v will be bigger because the potential energy that's a part of this is also converted into kinetic energy. So you'll have more kinetic energy at the bottom than you did at the top. We have m on everything, so those cancel out here. So we end up with gravity times height plus 1/2 v at the top squared, 1/2 v at the bottom squared. This whole side turns into a bunch of numbers. So let's do that. We're going to go 9.81 times our height of 15 meters plus 1/2 times 8.5 squared equals 1/2 velocity at the bottom squared. So let's get this mess of numbers going here. We've got 9.81 times 15. So we have 147.15 plus, we're going to say 0.5 times 8.5 squared. We have 36.125 equals 1/2 velocity at the bottom squared. If we add those two numbers together on the side, here we get 183.275 equals 1/2 v at the bottom squared. We need to get the velocity at the bottom by itself still. And so we'll multiply both sides by 2. 2 times 183.275. There we go. We get 366.55 equals our velocity squared at the bottom. So when we take the square root of both sides, square root, we end up with 19.1 meters per second equals the velocity at the bottom. So looking back at what we just did, at the top, we're moving at 8.5 meters per second, so we have kinetic energy, and we're 15 meters above the ground, so we have potential energy. Those two energies are both present, so we add them up for our total energy at the top. When we start going down the hill, we start gaining speed and losing height. So the potential energy is turning into more kinetic energy at the bottom until we're at the bottom and it's all kinetic energy. That has caused the speed to increase from 8.5 meters per second up to 19.1 meters per second. So I'm going to leave that there if you want to screenshot it. And then we'll do number 7. Any questions on number 6 before I erase it? Number 7, if we were in regular, like doing regular school stuff, we would be at, we would do a sledding lab. And our sledding lab would look exactly like number 7. So in number 7, we have our hill here. And the height of our hill is quite big. I don't remember what I have for it. Again, wrong thing. The height of our hill here is 35 meters. The length of our hill, so like actually hill, like the distance you'll travel going down the hill is 52 meters. And it takes 6.4 seconds to go down. And the mass of the person, we're going to say, is 65 kilograms. So I'm going to pull this back here. And so the first question asks, theoretically, what should the speed be at the bottom? Well, we know at the top we have potential energy, at the bottom we have kinetic energy. So we have mass times gravity times height equals 1/2 mv squared. We know that we can cancel the masses. We've done this rearrangement several times, and we get to the rearrangement of v equals the square root of 2 times gravity times height. So we can say 2 times 9.81 times 35 meters. So that's where we're sitting for the velocity if there isn't any friction. So if it's completely transferred from the potential energy we have at the top to the kinetic energy we have at the bottom, then the velocity that we calculate here is what it should be. So if you take this, you end up at 26.2 meters per second. If there isn't any friction and if there isn't any transfer of energy into other forms, that's how fast you're going at the bottom. I'm going to just double check my answer. Yep. Okay. So it's rounded to 26.2 here. That's part A. Part B says, now we're taking and we're saying, all right, we know that we're going to lose some, so let's figure out what's actually going on. So we're going to say that we have an initial velocity of 0 meters per second. It tells us that we go a distance of 52 meters and a time of 6.4 seconds. And we want to know what our final velocity at the bottom is. Yes, but I'm not putting a code in. So we need to figure out, using the big 4, if you've traveled 52 meters in 6.4 seconds and have started with an initial velocity of 0, how fast are you going at the bottom here? Equation 2 does that. We can say, that D equals VF plus VI over 2 times T. Here's the deal. Our VI is 0, so I can just take that out completely. So I have D equals VF over 2 times T. So to rearrange, I'm going to multiply both sides by 2. Cancel that off. And I'll divide by T. Cancel that off. So it leaves me with that VF is equal to 2D over T. Cool. We can do that. We can say 2 times the distance of 52 meters divided by the time we have of 6.4 seconds. Well, if we take 2 times 52 divided by the 6.4, that is not right. No. That's right. We get an actual final velocity of 16.25 meters per second. I think last hour I put in 53 instead, which is not right. I don't know what I did. So this is what we end up with here. And we have 62 or 16.25 meters. I'm going to just double check that again. All right, so that's how fast you're actually going. So here's what we're looking at. If there's no friction, we're going that fast. Reality is when we get to the bottom, we're actually going this fast because we have friction involved. So then part C asks, how much energy did you lose to friction as heat and sound? So for part C, we're going to take and calculate what the kinetic energy should have been, what that ideal is. And we're going to subtract what it actually is. And so we'll take 1/2. The mass is 65 kilograms times our ideal velocity, 26.2, and we'll square that. We'll take that number minus the actual, so 1/2, 65, 16.25, and we'll square that. So we'll calculate these two energies here. 0.5 times 65 times 26.2 squared. Here we have 22,309.3 joules. What it actually ended up being, so we have 1/2 times 65 times 16.25 squared, 8,582. I'm going to round it to 0.0. It's 0.03125. We don't need all of those decimals. So we're going to take what it should have stayed at minus what it actually was left. And so we'll say 22,309.3 minus 8,582.0. And so it ends up that of what we started with here, we had this left. So it means that in the way of friction, we lost 13,727.3 joules. And so that's what we're looking at. And like I said, if we were at school, we would have done this lab outside, and it would have, it just kind of would have made a little more sense in reference to what we had already done. But keeping in mind, in part A, we're looking at what should be happening theoretically. And then part B, we're looking at how fast we actually were going. And part C, we're using those numbers to figure out how much energy was lost in the way of friction, so heat and sound. Any questions on number 7 before I erase it, before my iPad fully dies? Go ahead and screenshot that. Then I'm going to be done sharing my screen. Take that off. I'm actually going to just log out of that because that's not going to keep going. So that's where we're at. Those are the pieces that we're working on. Hopefully with this, you can wrap up your practice problems and get those in and be done with that. When it comes to the quiz, those last 2 problems that are real goofy, those aren't going to be on the quiz. Those are ones, A, that show us what we can do, show us how we can make those connections and all the different pieces that go into it. But it's that heavy lifting that helps us kind of get stronger at what we're doing. So know that those last 2 problems, they're goofy. But I want you to know what you can do. I want you to experience them. It's not what we'll end up quizzing on, though. So know that the quiz will be similar to what you have on the first 5. So as you're wrapping up, 1, finish the things you need to. Practice problems, get them in. Quizzes, wrap them up, get them in. If there's a quiz you scored poorly on because you hadn't done the practice problems, and then you do the practice problems and you're like, I can do better on that, send me an email. I'll open up another quiz for you. You have to have the practice problems done. You can't just punt. Be like, yeah, maybe I get it farther this time. If you've done the practice problems, then I'll open that up for you and you can do it again. So keep in mind that there's options. Please, please, please keep doing your work and moving forward. I want you to be passing. I want you to be doing well, and I want you to be understanding what we're doing. So those are our goals right now. I'm going to hang on here if you have any other questions. Other than that, have an awesome day, and we'll see you later. Bye-bye.